Welcome to this machine learning tutorial. Today I'm going to explain principal component analysis. And what we'll go through in this presentation is what is PCA, feature selection versus feature extraction, how it works, and how it can be implemented using Python, and the different fields in which PCA is applicable in. So let's get started. So here I have a dataset that can be plotted on a one-dimensional space. So you have many different and various countries with its corresponding GDP, the gross domestic product. So what we can see here is that countries 1, 2, and 3 lie on the very right-hand side of the number line, while countries 4, 5, and 6 lie on the very left side. It appears as if this side is correlated together, while this side is correlated together. What if we have a data set that can be plotted on a two-dimensional space? So again, you have countries from 1 till 6, and along with the GDP, you have tourism. So you have the GDP, which is plotted on the x-axis, and tourism, which is plotted on the y-axis. You can see that countries 4, 5, and 6, again, are grouped or clustered on that side. And you can also see countries 1, 2, and 3 are grouped together on that side. What if we have a third dimension or a third feature? So along with the GDP and the tourism, we have infrastructure, which makes it a three-dimensional space. What if infrastructure is the variable or the feature that allows spreading out further of the points of my dataset? So as you can see here, what we're doing is that we're trying to identify patterns inside the dataset, where points, or as we have here, different countries can be correlated together. And we can see how the variance or the spread out of our data can be seen or can be analyzed. And that is PCA. It helps us to identify patterns in our data based on the correlation between our features. So, in a nutshell, and overall, what PCA aims to do is to find the directions of maximum variance. So it tries to plot the dataset and find out in which direction does my dataset exhibit high dimensionality. And it projects it on a new subspace with equal, but most likely fewer dimensions than the original one. And at last, the aim of PCA, as we have stated, is to reduce the number of variables. So its purpose is in dimensionality reduction. So it does so without losing too much information. And before we get into how PCA works and how it does so, we have to know the difference between feature selection and feature extraction. As we know, PCA definitely lies underneath feature extraction. So in a nutshell, before going through the slide, what you should know is that feature selection is choosing specific variables or specific features and deciding that these are going to be the features that I'm going to take under consideration when doing my analysis. So it means that there is a possibility when you're choosing specific variables that you're losing information that can be exhibited by other variables. However, in feature extraction, what it does is that it tries to create a new subspace that has a new set of data, and that data demonstrates high dimensionality across different directions. So it creates brand new features. And the most important thing is that it is efficient in the way that it still captures most of the useful information in my dataset. And the most popular applications is in algorithms such as deep learning. And deep learning can or most of the techniques are responsible for extracting useful representation of my input raw data, and that can be done through each hidden neural layer. So let's know how PCA works as an algorithm. So the first step here is that we have our data points. And for starters, let's use an example of GDP and tourism only. So we're going to plot our data only on a two-dimensional space, such for clarity and simplicity's sake. Then we calculate the mean of these points and allow the mean to be our origin. And there is an important note that you should know is that when you shift your data points, meaning that you've allowed the mean to be the center of your data, and as a result, the rest of the data is shifted, they do not say or do not state that or change how relative or distant they are from each other, meaning that country 2 is still on the far right side, country 1 is still the top, and country 6 is still the lower of the points, and so on. So the distance where these points are relative to each other is still doesn't change. So our question here is, we want to plot our first PCA. We want to decide which principal component will be the first principal component. And before I forget, the new dimension that is created in a new subspace are in the form of PCs, principal components. And to plot your first principal component, it means that this is the first principal component that demonstrates the very first or top high dimensionality or direction of high dimensionality of your data. So the first principal component tells you that this is the first direction of your data that explains the high variability in your data set. So here, if we plot this line, or we can have that line, or this line. Well, actually, this line is going to be our first PC that demonstrates the high variability in our data set. But before I make this decision, how did the algorithm decide or choose this line? This first PC, which is PC1, was decided upon the concept of the sum of squared distances. So what it means that you measure the distance between each point and the origin, and then you provide a summation of the squared distances. And this is called the eigenvalue. And the square root of the eigenvalue is called the singular value. So the sum of the squared distances for this line is very great. It's larger than the sum of squared distances between all the other PCs that we were trying to decide upon in the previous slides. So this brings me the highest or the largest eigenvalue. So as a result, this is going to be my first PC1. And then we have another terminology which is eigenvector. Eigenvector tells me what constitutes one unit vector of the PC. So the one unit is constituted of 0.88 parts of GDP along with 0.23 parts of tourism. So these components are what constitutes or constructs one unit vector of PC1. So we call it the eigenvector. So now that we have said or we have concluded what the first PCA is going to be, let's say or try to explain what the second PC or PC2 is going to be computed or constructed like. So let's agree that the first PC or PC1 is the principal component, that one that says that this says that or explains the first high or first direction of maximum variance in my data. And keep in mind, when we try to explain what the second PC will look like, keep in mind that PC2 is going to be the second top direction of maximum variance in my data. So how does PC2 is constructed, or how do we say that this is going to be PC2? Well, the line that is perpendicular to PC1 simply constructs PC2. And as always, what we do is that we compute the eigenvector and the eigenvalues of PC2. And the eigenvector of PC2 should be the second largest value after PC1, because we agreed that PC2 explains the second top variability in my dataset. Now, what if we have a 3-dimension space, meaning that I told my algorithm, or PCA, that I want the number of principal components to be 3 instead of 2. If you say to the algorithm that you want to reduce the number of features to 2, then it will compute the first 2 principal components. However, if you have a large data set and you tell the algorithm or state to the algorithm that you want to reduce the number of features or dimension of this data set to 3, then what it will do is that it will compute 3 principal components. The first one demonstrates the very top high variability in your data, and the second will be the second most explanation of the variability in your data, and so on. However, if you tell your algorithm that you haven't specified any number of principal components, or you don't know which dimensions you want to reduce your PCA, so you put a parameter input of none. So let's say you have a dataset of 13 features, then it will compute 13 principal components. But anyway, so let's say that you've stated clearly to your algorithm that you want to reduce the dimensionality of your data to 3 features. So it will compute 3 principal components. So it will try to compute the best line that demonstrates the high or the direction of maximum variability in your data, which is PC1. And then it will draw a perpendicular line to PC1, which is going to be PC2, which is the second principal component that explains the maximum variability in your data. And then it will compute PC3, which is going to be perpendicular to both PC1 and PC2, and so on, if you decide that you want more features inside your data. And the same eigenvector, or the same way in which the eigenvector and eigenvalues are computed as before. Let me say that the sum of squared distances, which is the eigenvalue, can be computed through using a theorem which is called the Pythagorean theorem. And I'm not going to explain this, which is outside the scope, but you can Google it, and if you want to know more about it, you can just leave a comment in the comment section below. How do you know, let's say that you have not yet decided how many principal components do you want to include inside your dimension, inside your dimensions, or inside your subspace? So you can, if you have a data set of 13 features, the first step that I'd recommend is putting an input parameter, which we're going to discuss using Python, as none. So you can say that I don't want to state an explicit number for the principal components to be computed. And what happens is that it tries to explain the variance of each principal component. So it can tell you that the variance for the first principal component is 62.5%. And the variance of the second principal component is 37.5%. And the variance of the third principal component is so on. So you can, by discussion, of course, and by analysis, you can decide upon how much proportion of the variance do you want to include inside your dataset, or you want to input in your model that you're going to use at last. So again, how can we compute the variance for the first PC? Let's say that we have the eigenvector for the first PC is 50, and the second eigenvector for the second PC is 30. So you want to know how much variance is explained by PC1. What you do is that you say 50, which is the eigenvector, the eigenvalue of PC1, divided by 50 plus 30, which is the combination or the sum of the total eigenvalues of all the PCs that you have. And by doing so, you can get the percentage of the variance that is explained by the first PC. So this is how you say that will be the variance of my first PC. And once you have the variance of all of your features or dimensions, and you decide upon the percentage or the overall percentage that you want to include, then that will allow you to choose the number of principal components to include. The last and final thing that I want to cover with you is the uses of principal component analysis. So what are the uses of the PCA? It can be used in facial recognition, in computer vision algorithms, in image compression. So anything that you want to, that has a data set of high dimension features, and you just want to focus on capturing the relevant or the information that is most useful for us. And it can also be used in finding patterns in high dimension data in the fields of finance, data mining, bioinformatics, and psychology. Finally, implementing PCA using Python is very straightforward. So from scikit-learn.decomposition, from that library, you import PCA. Here, I put as a parameter inside the model, the number of components or the number of principal components is 2, because I have already determined that I want to reduce the dimensionality of my dataset to 2 features. You fit transform the X-train and its corresponding testing, and then you start to explain, or you can use explained underscore variance underscore ratio underscore to get a clear representation of the variance demonstrated by PC1 and PC2 respectively. And once you've reduced your data, you can use a model just such as logistic regression, where you can start producing your insights and doing your analysis. And also, if you want an explanation on logistic regression, then you can find it as shown below. And also, please subscribe and like this video if you have got the concept. Also, if you have any comments, please leave them below. So this is an overall and very simple explanation of what principal component analysis is.